not least, Jeff Dean. Jeff Dean is a chief research scientist at Google, and I had a privilege to get to know Jeff Dean a bit when I was at Google DeepMind, and he was always the champion and supportive of research in ML for system, including my research back then. So, and thank you everyone for being here. I think that it's really great that you dedicate your time to be on the panel, even though it's on Sunday, and I'm very excited to get to have a discussion with you. So the topic of our panel today is about the past, present, and the future of ML for systems. And I have prepared some questions, but I also would love to hear questions that the audience might have. So if you have questions, you can go take the picture of the QR and enter your questions in the chat. And we might not be able to go over everything, but I'll try my best to cover most of the questions people might have. So let's dive into this, and we're gonna start from the past, kind of like retrospective, a lesson learned. And the first question that I have is that looking back at the, in the field of ML for systems, what do you think is the biggest achievement an advancement that we have seen in the past decade? And why did it go well? What went, right for that particular project or direction? So how about we start from Tim and we go towards that direction?
I don't have one particular research insight which I would highlight. Instead, I think just that machine learning now is used in the critical path in most systems, I think is probably the biggest achievement in that regard. And it's just one single technique. It's just how the things are combined and that we see it really happening, scheduling decisions made based on machine learning predictions. Learn query optimization technique, which we use machine learning models to figure out what is the best query plan. Hardware designs, there's so many examples by now, and I wouldn't say it's one thing. It's more this happened and so quickly happened. 6 years ago, I still remember that there was a discussion, not for this workshop, there's another SysML conference where they said machine learning for system is not a thing. You shouldn't work on that. And it just changed very, very quickly, and now it's mainstream.
Yeah, I was actually pretty inspired by the work that Tim and also you have done in 2017 around, so that was sort of eye-opening. At that time, I remember we were talking to some of the product teams, and they were saying, every time we change to a different SKU, and then we have to kind of tune the system all over from scratch, and everything, there's a lot of regression. Is it possible for us to do it more automatically? It seems like a very challenging task and takes engineers months to actually get back to even the same performance as the previous SKU. Suppose you get much better. And there are certainly a lot of low-hanging fruits because the complexity of the systems already exceed the capability of engineers, and our methodology has been a little bit outdated, to be honest, and there's a lot of dynamism once we get to the certain level of complexity. And we certainly have a couple projects that have some success, but maybe later we'll talk about some of the limitations and challenges.
Yeah, I think I'm just going to second what other folks said. Obviously the RL for chip design stuff has been incredibly impactful and very exciting. It just feels that there's a lot of value to be unlocked by applying machine learning for systems. I heard of a possibly apocryphal story of a student doing an intern project at Google where they predicted the compression rates for YouTube videos so that they could be distributed more efficiently, and it saved somehow billions of dollars from an intern project. So I just, not sure if true, but I feel like it speaks to the fact that there's just so much value to be unlocked by using ML for these kind of problems, and it's really exciting.
Yeah, I think it's hard to point to one particular thing over the last, say, 6 to 8 years, but it's very clear now that 6 to 8 years ago, people were very skeptical and weren't really trying learning in the middle of core computer systems. And I think what we've seen now is actually a progression and a very broadening of what people think about in terms of how they can tackle it. I think initially people would dip their toe in and say, maybe I can learn, how to tune my flags or something. And then people got it more into maybe I can do a much more end-to-end solution for some sort of problem. I think in hardware design, I talked about in my talk, there's good work on many different phases of chip design, but I think there hasn't yet been kind of a progression to applying it to a full end-to-end system yet. And I think Tim and I were actually just talking as we were walking over about, could we do this for software systems as well? Could we, take a high-level specification and figure out how best to run code and actually have the system generate the code and generate the way in which it's going to run? And I think that's a pretty interesting direction as well. So, yeah.
Awesome. So, but yeah, it's very inspiring to see like how the field have grown in the past decade, and now people like truly believe that hey, there's actually room that we can fit like machine learning in system. But on the other side, have you also like in your experience working with production system, real system? What do you see that is still kind of like limitation or kind of like the pushback from people that they still feel that, oh no, like this is not like the right thing that we should apply machine learning? And do you think that they are they right, or like is there something we can do to actually like make ML for system more prevalent in these productions, like very large scale systems? Maybe we would start from that and go to this direction.
I think there's definitely varying degrees of skepticism or concern about some of the aspects of automated control of, say, online production systems is one area I've seen, not irrational fear of like random ML models doing changes to my production systems and like deciding we only need 20 backends instead of 50. When maybe that might not be right. There's fear of, I think, changing the operational aspects of how people actually manage large-scale systems. So I think the right way to approach that is to sort of install some safeguard ranges. Maybe your ML model can only predict within a certain range that is known to be sort of reasonably safe, and have then more comfort established as the system starts to operate in that range and people see it actually does the right thing, and have it experience like some weird conditions that it's never seen and it reacts well, or maybe it doesn't react well, and then you iterate and fix things. So I think that's kind of the right way to build trust with people who are skeptical.
Maybe we do like one more answer and move to the next question. Anyone want to take on that?
Like two things which I think like are always surprising to me in like transitioning thing to industry. One is like regressions play much more an important role in that sense. And like if you roll something out and you regress even some of the customers you have, those are the ones which call support. Those are the ones which complain the most. Those are the ones which probably will cause you that you roll back potentially even the feature, right? So like in how to deal regressions and how do you know which areas you are impacting in a negative way. That's like one thing, and maybe there can be more done in that regard. The other one is like, I think at least when I look at the papers, they always tend to be much more complex than they would have to be, particularly in industry. So like when we write a paper, we tend to do a complex solution which is scientifically interesting. Even the very simple stuff can make such a huge difference in practice. It's like there's something about simplicity which often wins. And before I touch even RL, I try lots of different things before, because RL, to get it really right, it's so finicky. There's like the models we, for example, use the first and best way to predict, for example, a query resource consumption is a cache. That was an insight on its own, a cache, right? It's very simple. The next big thing we use is like a simple boosted decision tree. Very fast, very reliable, very easy to debug. And we didn't even really touch the very complicated things yet, because the benefit we get from them is like minor compared to everything else.
Okay, the next question, moving on to more the negative side. I also want to hear about like in the past, experience applying ML in system. What is like the biggest lesson learned that didn't go well? And like how would you approach that differently today or in the future?
Can try to answer that question. I think there were actually a lot of lessons. I think Jeff and Tim actually mentioned some of them. We actually experienced about the same kind of phenomena. And one of the things that we learned is that the way we approach incorporating ML is actually quite disruptive. We have to basically tear apart the system, and it's not very natural because it doesn't fit into the system. It's sort of an afterthought. So now we're really thinking about how we can design the system so that from the beginning we thought about how to incorporate machine learning and AI technology. I think that will make a huge difference. I think one of the things that we realize is it's not just applying AI on some system problems. I think a lot of system thinking is actually very critical when we design this coexistence of AI and systems. And that's where I think we need to develop new methodologies, not just there's one problem in system that we want ML to solve, and then we just plug in a solution. That doesn't work.
Maybe just adding on to that, I agree with you. Like, often people want to put ML into a system, but it's actually pretty hard to, as you say, rip it apart and figure out how to put it in there. Our experience, that was part of the motivation for the smart choices thing that I mentioned in the talk, where you have this pretty nice, simple API for inserting learned choices of various kinds in the middle of sort of existing crufty piles of C++ code that you don't want to rip apart. And I think that we should do more of that kind of abstraction building, that people can then put learning in all the right places without having to do too much surgery.
There's also the resource management part. I think I was going to ask you about the smart choice. The interface is beautifully done. Thanks.
All right, thank you. And I'm gonna read out a question from the audience. So from Alexander, they said, we have heard in the first half of the day, you share patterns you have observed in your work on ML for systems. Could you share any patterns you observe in people working on those systems, like maybe your younger colleague or PhD students? This is not only the notion of productivity in system that is changing, for example, time to produce a chip, but also productivity of humans. As a researcher, it's get harder to even stay up to date with the field and then do a novel research at the intersection of ML and system, publish it, get money support behind less popular direction that is not LLM, for example.
Yeah, I think it's easy to get overwhelmed by the flood of papers that are being released, and you can kind of get in your head about keeping up with every single thing that comes out. But then again, I'm continually surprised of, it'll happen to me that I'll have an idea for 4 years before I get to it, and it's still relevant 4 years later, even in this climate. So I think there's still everyone wants to pile on to the hottest topic and go off of there's one big paper and there's this is not a systems paper, but SayCan. The summer after SayCan came out, every single intern was working on a SayCan clone. But if you just go a little bit off of that super popular manifold, I think there's still a lot of room to contribute, and kind of going back to my other point about a lot of interesting systems problems that are underexplored still. That's kind of how I feel about it.
Yeah, I mean, I think the questioner's sentiment, they shouldn't feel bad about that sentiment, because it affects everyone. There's no way you can possibly keep up with the field of AI, let alone the AI for systems work even. That's now become a pretty broad and thick vein of hundreds and hundreds of papers. So I think what you need to do is kind of keep track of what is going on in the community at a high level. You don't need to read every last paper in detail. Sometimes you do need to know because it's very related to what you're trying to do. But I think it's often better to have kind of a sense of what's going on by skimming 100 paper abstracts than spending the time to really deeply read one particular paper. Because what you want is this constellation of ideas bubbling around in your head of what's possible now. And then when you go to tackle a new problem, you're like, oh, that sounds a lot like these 3 other things that I already know about, and then there's some other hard problem I might need to solve to do this thing, and then you can kind of put all those things together and really sort of move forward.
Yeah, maybe I just add one point. I think this is just phase that we're going through because there are a lot of exciting ideas to explore, and everyone has his or her own idea. But I think we probably could get to a stage where there will be, we see some convergence, and there's some structure and some clear directions that we'll be focusing on. So just stay on.
And I'm going to read out another question from the audience, from Melissa. Do you think ML is an overkill for some system problems? If so, what are they? On the other side, what are some of the good system problems that are interesting, suitable for ML solution? I guess we also cover a lot of that already in the morning, but I'm also very curious to see what you think about like what is overkill for ML solution.
Yes. I mean, like, in the end, you need to use the right tool for the right problem. To give you one example, and again, I need to read the paper here, but like originally I always thought that like query optimizations, like it always is the question like, should LLMs do that? And I would always say like, no, there's no way that this is the right tool for it, because you need to know something about the data, the statistics, how the join behavior is, so you need something very, very specialized for that, and you shouldn't do it. There are many other algorithms, like we tried like impacting joins, we got little gains, but the complexity we introduced by that was so high that I would also strongly recommend against implementing that right now in an actual system. And this might change over time, but like it's like particular, like right now, if I want to transition something into production, I'm looking if it's like simple enough, can I explain the decision making? How do I debug the whole thing? If something throws up in my face, how do I know how to debug it? And if the answer is like, okay, the complexity is so high, probably the payoff is not big enough, then simply don't do it. Right? So there's certainly a lot of problems where it doesn't make sense. And then there are others where the gains are huge, really big. Like resource optimizations just being one example.
Yeah, my experience is that we shouldn't really try to replace system components with ML. One of the examples I actually talked about in my keynote on Thursday is that we're trying to create all this try to optimize collective communication library for different scenarios. And initially, we use this powerful GPT-4 and try to generate the code directly. That didn't work very well. So what we did is we actually create a simpler abstraction for LLMs. Essentially, just create the schedule, and then we will use the compiler, which is something that can easily build for that specific domain-specific language, and that's accurate, and that the whole system with ML generating the algorithm, the schedule, and system validating that schedule, and then generating and optimizing to generate the code. I think that's much better than throw everything to ML. Like even the large language models cannot handle some of the complexity, and that's not necessary.
Yeah, I think it's worth pointing out that to some extent the incentives of getting a paper published in NeurIPS and the incentives of getting a system to work are a bit misaligned, right? Because if you do anything too domain specific in your NeurIPS paper, the reviewers aren't going to like it. This isn't your general algorithm that works broadly for every problem. But if you actually want to get a system working, it's happened to me over and over, the more you build in domain knowledge, the more effectively it can work. So I think it's just interesting to consider that point.
Yeah, I agree with that observation, and I think one way we should do this is adjust as a community and reflect, work that gets into a production system and has real insights should be valued maybe more than it is. I think it's really good to look at what is the potential gain from using learning versus the current approach, whatever it might be. If the current system already works pretty well, and the consequence of the decisions and choices you're making, are not like 10x or 100x, they're more like 10%, then that's probably not a problem where you need to apply ML. But if you have something where, a wrong choice is 100 times as expensive as the right choice, and perhaps online observations of what's happening in the system would help you make better decisions, that's the kind of thing you really want to be looking at it from wow, that's a really ripe problem for online learning or something.
All right, thank you so much. Let's move on to the now and the present a bit more. And I think this is like a good leeway and follow up with that question on kind of like, okay, should we move from like the system component into like ML component? Well, now we see in the breakthrough of generative AI, right? And you also see that in the system community, we are also moving into like investigating if generative AI is a good solution for system. And more paper in ML for system is now using generative AI. So what's your thought on that? It's kind of like now like, oh, should we use, very specialized ML model, or like should we go with LLM, right? Because in some way, I think like this era of LLM, it also makes it really easy to actually fine-tune the model. For example, like at OpenAI, I think like we recently released this API that you can just, throw your data into the model and like, code up the grader for the RL environment, and then you get the reasoning model to train on your data. You don't even have to like code your model using PyTorch or TensorFlow or Jaques anymore, right? So like, what's your view on that? Like, should we like move towards using that, or like, is there room for like very specialized, very well-designed model and the environment for that particular system?
I can actually take this one. I've done a bunch of papers recently where we were tested. It's very easy to just play with prompting and test, like to what extent can an LLM do this problem? So our recent paper on the traveling salesman problem, we just prompt LLMs to see if they can solve traveling salesman's problems. Turns out, of course, they can't, right? It's so often true that training a smaller model on a very specific use case is still much more effective than trying to prompt a lot larger model. And of course, trying to do inference with an extremely large model is itself a very challenging systems question. So it seems like you might just be introducing more problems than you had in the first place if you try to do this, kind of building on what Lidong also said. So.
Yeah, I think I was listening to Tim's talk this morning, and I think I probably went through the same journey about LLMs, and I was actually amazed at the capability of LLMs as we start experimenting with some of the problems that we're facing in systems. Initially, I think we were using RL to solve some of the allocation, resource allocation problems, and managed to get it to work. But when we tried with LM, it actually does some of the RL components, probably because the RLHF stuff that Natasha actually worked into those large models actually has a very effective, same kind of effective optimization capability as RLs, but it has this domain knowledge that they managed to leverage. What's interesting is I think there's probably going to be a shift from using ML or AI to do optimization to use this as a sort of intelligent partner in system design. We see that coming. It's not there yet. As Natasha said, it makes stupid mistakes, and when you just use prompting, it doesn't do very well on most of the tasks. Anything difficult, it fails. But we also see the potential when we do a little bit more work, doing some sort of fine tuning, and coupled with new kind of methodology with systems, it can actually do much more than we observed in the past for individual ML components.
Again, I think it comes just down to use the right tool for the right problem. If you want to build a scheduler, don't use an LLM code to make your scheduling decisions, right? Like it's just not the right tool, right? Like a very simple model is the right thing. It's the same thing if I need to transport a whole bunch of plywood. I recently started woodworking, so I transport plywood now. If I need to transport plywood, a Tesla is a shitty car for that, right? So you rather want to have a very reliable truck. So use the right tool for the right problem. And I don't have a truck yet, which really sucks, but yeah.
Okay, and then I think this is kind of orthogonal, but it's also related to how we can actually make people adopt ML for system more widespread. And I think Tim kind of mentioned this a little bit in terms of kind of robustness and reliability of the system, right? Do we still see, I think that we still see, people afraid of using ML in the system because of explainability. Right? So what do you think that is the thing that we can work on to kind of address that? And this is also one of the questions from the audience, from Kirill asking, like, how much does the ability to explain ML decision play a role in convincing correct stakeholders into adopting ML methods in existing systems?
I mean, I think it actually is not a uniform answer. I think for some kinds of problems, it's really important that the system have some explainability aspects to it, because it's part of a much larger system that the interactions of this module making decisions affect lots of things. And there's both, humans and other software and other ML models involved. And there you want some explainability so that the people who are sort of ultimately in charge of operating that system can actually, understand what's going on. Same reason you want monitoring software for non-ML things. Like you want to understand and measure a bunch of things and then be able to understand what are the interactions that are happening here. But I think there's other things where it's less important that you have explainability. Like if my malloc just magically works better and, the allocations become faster and there's less fragmentation, I don't think you need too much explainability for that kind of thing, because it's sort of a fairly isolated thing. It doesn't really affect the rest of the system other than in a positive way.
I actually agree with Jeff on this, but I just want to point out a different aspect of it. Like one thing which I think hinders the adaptation of like ML for systems, like techniques, is essentially how the ML research team works together with engineering. Right? Like it's like the engineers which are currently owning the systems, they do the day-to-day operations, they build very robust systems with a lot of testing and are plugged into this ecosystem. And now if you come along as an ML researcher and said like, hey, I have this really cool idea in the Python notebook, please take it and implement it. Like, this is not going to happen. So it's a question just like on how you structure even like the implementation process, on how the team is embedded to make it happen. And if this fails, like there's not enough trust, and I fully understand that. If I have to run, let's say, a database system, operating system, a key value store, like, and somebody gives me this like very fancy RL thing written in Python with a bunch of question marks, like they will not take it, right? And so often it comes down to on how these teams work together and have potentially even co-ownership, right?
Part of that trust can be interpretability of the model.
Part of the trust can be interpretability, but it's not the only thing. It's just like it's one aspect of many, exactly. And it's actually really hard to get that trust. So start small, like we did the first small feature first, we got trust by doing that. Then you take the bigger one on. And now so my research team I lead at Amazon, they are partially on call also for the features we built. Because we just said like, no, if there's something going wrong here, we are on the hook to really figure out what's wrong. So it's not like handover of this Python notebook, right? This normally never works. And so on one hand, there are techniques which are important, but then there are also just like the organizational aspects to make it happen.
I'm also curious to hear from Natasha, because was one thing you mentioned in your talk about like adversarial learning for kind of like robustness and reliability, right? So like, do you think, what's your view on that for like system area?
Yeah, I think the dream of sort of this multi-agent adversarial training, so I've been working a bit on this unsupervised environment design problem where you have one agent pose a problem for the learner. And it's playing this like mini-max regret game. And we have some nice work that has theoretical results saying like, if this game converges, then your learner should be playing the mini-max regret policy for any example that your generator could come up with. So it's like very nice. But the key there is if it converges. So the problem with deep multi-agent reinforcement learning is it's actually often not guaranteed to converge. So while that would be, and I'm actually really interested, by the way, in applying this kind of idea to LLM safety, although this is not a systems question. I think it's a really powerful idea, but the question is that enough to generate trust? We have some theoretical results. This could be nice in theory if it converges. Maybe not, right?
All right, thank you so much. I think we only have like 10 minutes left, so I want to move to future, more future forward looking. And I would like to hear what you think about like where AI would be in 5 years from now, and what would that look like, and what is the implication on how we build the system? Sorry, it's a hard question. There's no right or wrong answer.
Yeah, I mean, I think it's often hard to predict the future. I do think we're making a lot of progress as a field, and we're starting to see more ambitious uses of machine learning for various kinds of systems. The end-to-end chip design thing that I sketched out in my talk is not something that exists today, but I would hope in, 2 years, 3 years, 4 years, 5 years, we've made a lot of progress in that direction where you can actually have a much more end-to-end learned, machine learning system that helps tackle a really difficult, challenging systems problem. I think that's probably true in hardware. I think it's probably true in how do you decompose, very complex, high-level requirements into sort of individual pieces of software that are all interacting and running. I really like the multi-agent setup and framing that Natasha had, because I think actually a lot of software systems we've hand decomposed as people into separate subsystems, so that you have one team that's doing the spelling correction system for a search system, and then you have another team that's doing crawling and indexing, and they have APIs between them. And it seems as though maybe we could get to a world where you have software agents that are learned, also performing some of those roles and interacting with other people and also with other agents.
Yeah, I think, first of all, I think we should start working on more aggressively on harder problems. So I think I listed one in my keynote, which is, in systems, verified system is always a sort of holy grail. A lot of people have been working on this. We really want to build systems that are completely trusted, verified. And I think there is hope that the combination of AI and systems will allow us to get there. The second part is I really feel like we need to develop a new set of foundations for sort of AI plus systems and maybe new methodology. I remember when we were looking at incorporating learning into systems, one of the things we want to manage is the complexity. Right? The whole monolithic system is too complex. Even when we apply machine learning, we try to tune those parameters, and we're trying to figure out whether there's something similar to modularity that allow us to manage complexity or to think about the systems. Maybe now today, Natasha's talk makes me think maybe this multi-agent framework is the way to kind of divide and conquer. Because systems, in my view, is always about managing complexity, and we have many ways to do that. So in this combined world of AI and systems, I don't know what is the foundation, what are the methodologies that we can use, because we're not going to only deal with toy problems anymore, right? We're going to actually look at the whole system. Jeff was talking about the whole stack, but I think it's certainly too complex even for AI. And we really need better system thinking and tools and even principles. And I think we'll see that probably in the coming years.
I'll ask a follow-up question. So this is like some of the fear I have, right? Where like I start to see people rely more on, generative AI and LLM to like help developing their code, right? And like we are envision this dream that, one day we, as an engineer, we just, come into office and like describe, like think about like high level, hey, we want to accomplish this task, and then we just like delegate to the agentic generative AI to, do all the coding to ourselves, right? But like, how can you really trust that it's actually doing the right thing, right? Like thinking about the level where like, if we actually achieve, like the AI is actually like achieve like human level intelligence or even higher. Like as a human, how can we check their code? Like how do we actually validate that, right? And what does it mean to like use that tools to build a robust, reliable, and we can actually trust the system?
Yeah, I think that's a really excellent point. And just building on what you both were saying about the multi-agent idea of modularity, the only reason modularity is good is because you can decompose the problem into testable components and verify that they work. So for any system, in order to increase the trust, we actually have to have good ways of evaluating each component and understanding how it's contributing to the larger system, rather than just making a more and more complex system that we have no insight into.
While I totally agree with all of that. We need to do something regarding the correctness. At the same time, like always when these big visions are mentioned, oh, the LLM models will help to write the code, there are always all these concerns around it. To be really frank, I'm not that much worried about them because I see what it does to my son, for example. So my son, his birthday last year, he wanted to have an LED panel, like one of these like little LEDs you can program, connected it to an Arduino, and asked me if I can help him to program it because he wanted to have his name running from the left to the right. And I said, like, I'm happy to help you, but I first have to finish these like very important quotation mark meetings, right? So I went to my meetings, 3 hours later I came back down, and he had running his name from the left to the right on the LED panel. And I said, like, how? How did you do that? And he said, like, oh, wasn't that hard? I went to ChatGPT. I asked to program then that thing. The first version didn't fully work. Then I did this and this and this, and now it works, right? And if this is an 11-year-old, never has done anything more complex than with Arduino and LED panels yet, pulling that suddenly off, this is a game changer, right? And therefore, it's for me also so hard to predict what will happen in 5 years. This is a game changer. Like, it changes the way on how people overly learn today. And this thing might not have been completely correct, but that he got that far is amazing, right? And now we will figure out more of the rest and like do the testing properly. And there's a lot to be done, but still, it's amazing.
I mean, I think that's an illustration of what's likely to happen, which is, people are worried about, well, we need software engineers if this can be done. But I think there's just a huge amount of things in the world that software could help the world with that we don't do right now because it's not really economically viable to make software for that particular thing. And I think what's going to happen is we're going to have a lot more software systems in the world that do different kinds of interesting things because they're going to be easy to create for people. And then they're going to interact with other software systems. So that's going to be a very complex and pretty different world than we have today because there's going to be, maybe fully automated or mostly automatedly developed kind of smaller systems that do something someone cared about for their particular thing where you would never write a custom software package for 10 years ago.
So basically just embrace the change and then we adapt accordingly. Although one thing I wonder, maybe this will be like the last question, is that, but as a system researcher, which I think many of you have like the system research background, do you think that we should start thinking about how we can actually build system in a world that now we're gonna have AI agent actually interacted with your computer in whatever way a human can? Like, you think that require like a different design to the systems, or like we just kind of like try it out and see what happens?
I mean, I think you can have different interfaces for software systems to interact with other software systems, but the most likely way to have broad impact is if the software system can use the same interfaces that have been built for humans, right? Because not every software system is going to have modifications made to it to enable some weird side door for the system to get at it via an API or something. If you can like control a mouse and a keyboard with an agent, that will enable you to do anything a person can do on a computer. With safeguards, of course.
Yeah, I think actually for the system community, we have been dealing with the trust issue for decades. And I mentioned that there is this notion of trusted computing base, right? And I think, to me, the trusted computing base is probably going to be outside of LLMs because I don't really trust whatever LLM generates. It's pretty good, but we can't completely rely on it. If we can solve the verified software problem to some extent, at least for some programs, if we have some verifiers outside of the AI, then we can do a lot, right? In systems, we always do, we trust but verify. So we verify a lot of results, and we can create a lot of verifiers. And to the extent that we trust the world today, we can have hopefully the even higher level of trust because of the mechanisms we put in place.
Can I add one more thing to that?
Yeah.
I mean, I think one of the ways you get really high quality software with humans writing the software is you have really good processes for developing that software. You have extremely good testing that covers a lot of the things you want the software to do. You have code reviews by another person who is looking at the code and understanding it and making suggestions. I think it's worthwhile thinking what roles can software agents play in this setting as well. We already at Google have a bunch of ways in which sort of we have machine learning models of various kinds, like also suggesting code review comments during our human-to-human code review. We have LLMs interpreting human code review comments and actually trying to figure out how to apply them so it's easier for people to actually accept code review comments. Suggesting test coverage kinds of things is an important area. I think there's actually a lot we can do to make multi-party or multi-agent settings that actually create robust software by mimicking some of the things we've come up with as human software developers.
All right, thank you very much. I think we are at the end. We are a bit over time, but I want to thank you all the panelists again for being here today and everyone for attending. And I just want to wrap up with one quick last questions about what are you most excited about in the next year? Just one sentence to end with a positive note.
I want to see how far we can get on end-to-end chip design.
Marl for LLMs.
Verify systems.
Skiing in Italy.
All right, thank you everyone. And we have a break and we'll come back at 2 p.m. for a series of talks on code generation. Oh yeah, and sorry that there's a lot of very interesting questions that I